All right, here's 2-2, day 1, just entitled Functions. Keep it short and sweet. A fitting section for, a class called Functions. Essentially what's going on in this section is we are taking a step back from kind of the specific algebra details that we tend to do, specifically with lines and quadratics so far, and to kind of talk about functions in a broader sense about what they are and their characteristics and just some general things about them that we should know. Okay, starting with, a definition. A function f from a set A to set B is a relation, okay? A relation in math is any way of basically pairing two numbers together, okay? Actually, in some cases, can be more than two numbers, but in our case, we'll say two. It assigns elements of x in set A to exactly one element y in set B. Okay, the set A is referred to as the domain. You could also call it the inputs. You could also just call it the x values. The set B contains the range, the y values, or if you want to call them the outputs. Okay, you'll see a lot of what we call mapping diagrams that kind of illustrate this. It's like, all right, here's x. That big circle represents your domain. Over here, here's all your y values. We call that your range. And then you've got like different numbers. Let's say we had like 1, 9, and 4 over here, and 3, 1, and 7, Here's our function f. 4 goes to 1, 9 goes to 7, okay? That would tell us with this particular function, if we were to graph it, it goes through the ordered pair 1, 3, it goes through the point 9, 4, and it goes through the point 4, 7, right? The arrows themselves, that would be the function, okay? That's how the elements, elements is a general term, numbers in our case. We tend to work with real numbers when we're dealing with functions. It's how the numbers are paired together, okay? For example, if you had like a line that was 2x plus 1, okay, that function would take your input, or your x value, and it would double it, and then it would add 1, and that would determine the y value. Here's another mapping diagram. Okay, there's really nothing to draw out or work on here other than to explain that you should know you see functions all the time. Okay, you don't always process them or think about them the way we do in a math class, where we get kind of analytical about how we write about them and how we communicate them. Notation like f of x and all that kind of stuff. But temperature, just one basic example, and we could give countless ones. Temperature is a function, okay? So like the deal is, as you're looking at this mapping diagram, okay, to be a function, each time of day, here's 1 o'clock, right, can get paired with one temperature, right? And if you're in a single location, you can, and you take the temp at 1 o'clock in the afternoon, you can only get one reading. To get a different reading, you'd have to move, you'd possibly have to move to a different location. Temperature is a function of time. Okay, we don't think about it that way when you're looking up the weather, but it is, all right? Looks like from my diagram, at 2 o'clock it was 13 degrees, 3 o'clock it was 15, 4 o'clock it was also 15, at 5 it was 12, and at 6 it was 10, okay? This scenario right here often leads people to think that this violates the definition, but it doesn't, okay? Two x values can go to the same y value. Okay, just to look ahead, you're going to see it on the next slide. If I'm looking at a mapping diagram and I'm going to say, hey, wait a minute, that's not a function, what I would look for would be something like this. okay? That would be an element of set A, or my domain or my x's, with 2 arrows going away from that number. Okay, in this case, that would mean at 3 o'clock it was 8 degrees and it was 11 degrees. Well, no, it could have been one or the other, but you shouldn't have 2 temperature readings for the exact same time at 3 o'clock. Let's continue that down here, okay? This set of ordered pairs does represent a function. Okay, I'll show you that in those exact same terms of just putting together my mapping diagram. Here's x, here's y. Okay, if I relate it to the mapping diagram, the case that we just talked about in the previous slide, we shouldn't see it. Okay, we shouldn't see a number from the x part of the diagram with 2 arrows leaving it. Now I go through the ordered pairs here, and I'm just looking at x coordinates. We've got -2, -1, 0, 2, and 4, right? According to those ordered pairs, that's my domain, or all my x values. For the y's, I have 1, 3. 1 gets repeated. I don't need to draw it a second time in the mapping diagram. I have 5, and I have 7, okay? Now the arrows need to show me how these numbers are paired together. From the first pair, I can see that -2 gets paired with 1. -1 gets paired with 3. 0 gets paired to 1. That's okay, right? The deal is 0 has to just go to one number. It can go to the same number that another number is going to. In this case, -2 and 0 can both go to 1. It's still a function. 2 goes to 5, 4 goes to 7. Again, I'm looking over here at my x's. All 5 of those elements in my domain, they each have 1 arrow, right? Again, it's going right back to our definition of a function. They're getting paired with 1 y value. We'll call it a function. Here we're going to use the mapping diagram to show that this isn't. Same way of going about it. -2, -1, 0, 2, and then 0 shows up a second time. For my y's, I see 1, 3, 1 again, 5, and 7. Okay. Again, -2 goes to 1. -1 goes to 3. 0 goes to 1. 2 goes to 5. 0 goes to 7. Okay, and there you see it. That, in a mapping diagram, that is what we're looking for. This case with the x value 0 that has 2 arrows, right? And you see it show up right here. It's getting paired with the y value of 1. That's great, okay? But according to the definition of a function, that means the only y value 0 can get paired with is 1. And then it goes right over here and says, hey, wait a minute, I'm going to get paired with 7. Okay. It's a relation, right? Because we just have a method of pairing numbers together. And now that I think about it, a relation, I said it could pair more than 2 numbers together. You could have repeats, but it really is about pairing 2 numbers together. But just a relation, that can happen. A function's a specific type of relation. So we would say here, that mapping diagram is showing us not a function. The blue one over here, that's a function. We've already used it a little bit, but a lot of times we'll work with what's called function notation, where we replace y with f of x, right? The reason we do this is it we can more easily communicate what's going on with the ordered pairs that our function has, right? For example, f of 2, okay, if I wanted to get that, I would go negative 2 squared that would be negative 4 plus 8 plus 1, which would be 5, okay? Short way to write that would have been f of 2 is 5. This notation tells you if you put in that x value to the function, it gets paired with that y value. If you were looking at it graphically, you can tell that function's a quadratic, so its graph would be a parabola. It's going to go through the point 2,5, okay? We know that because when we put in the x value of 2, we got the y value of 5, okay? But be prepared to see this. You could plug a variable in. Wouldn't matter. I could switch x to m, which is kind of nice. That what that really means is if we're doing a word problem, and if x represents time, right, and we want to call it t instead of x, it doesn't change the meaning of the function. You can change the letter that you're using as your input. Okay, right here, this problem doesn't have a context to it, but I took x and I switched it to m, which I can do. It wouldn't change. Like, you'd still find if I put 2 in for m, it's still going to get paired with 5. Over here, it looks like I'm putting a function into another function. Which you can do. It might leave you with some simplifying. I could plug in x plus 2. And I'm going to simplify this and see what I get to. 4x plus 8 plus 1. Let's see. That's some foiling to do here. That'll give me x squared plus 4x plus 4. Over here, I've got 4x hanging out there and plus 9 at the end. I'm kind of burning through this one. You could certainly pause to catch up if you needed to. Feel free. So I got a couple like terms in there. Negative 4 plus 9. Okay. Negative x squared plus 5. Plugging a function into another function. You can do it. It's a thing with functions. It's called composition. I haven't looked far enough ahead into our schedule. My guess is at some point in time, it could actually be in chapter 2, we will specifically address what's called function composition. More details on how this works and when you would do it, especially in a word problem. Like, why would a function get plugged into another function, okay? Because really what you have here is you plugged a line into that quadratic, a line that had a slope of 1 and a y-intercept of 2, okay? For now, in this section, we're just saying, yeah, you could do it. You could take your x variable, I could plug in another function, and I could simplify it, and in this case, I got negative x squared plus 5. Gotta zoom out here a bit. All right, for the remainder of this lesson, we're going to talk about domain, okay? When you're working with a function, it's really, really good to know its domain. Okay, there's a couple different ways you could look at it. What we'd say symbolically or graphically. I'm only going to take you through today and have you look at it symbolically, which means can we tell all the possible x values that we could use just from looking at the equation, okay? It's a different ballgame if you're given a graph. If you're good at graphing, it's actually a lot easier to identify the domain off of a graph, but we're not going to do that here. It's the set of all real numbers for which the expression is defined. Okay, translation. If you put an x value into the function and you get an answer, it gives you a y value. That x value that you put in is part of the domain. Now, in one example, a little bit later on, I'm going to contrast what this definition of an implied domain. Sometimes you'll hear it called a theoretical domain. It means you're talking about domain apart from any context. Okay? A function's domain can get more restrictive if you're dealing with a word problem. Okay? Hang on to that thought. When we get to the example where that comes up, I'll show you. Okay? Here we don't have the equation, we just have a bunch of points. So I'm like, okay, -3, -1, 0, 2, 4. I just list off all the x values. That's what I'm going to call my domain, right? I don't have the equation there, but if I just have the ordered pairs, I just need to collect all the x values together. All right, I'm going to classify this one, because this is just a good one to know, right? That function right there is linear, has a slope of 4 and a y-intercept of -11. Now, instead of sending you on a wild goose chase of trying to find an x value that doesn't give you an answer, I should give you the heads up. With lines, you won't find them, okay? Always, always, always. Well, I shouldn't say always, always, always. I can think of literally, we're not going to talk about it today. I can think of one case with lines where its domain isn't any real number. In fact, if that makes you curious, think about that yourself. See if you can go find that. Just off the top of my head, I can think of one case with a line where its domain is not all real numbers, okay? If you can figure that out next time we're in class, let me know if you think you've got it. But it's pretty safe to say there's a bunch of different ways you can say this. Okay, if you want to write it that way, that's fine. Whoops, I shouldn't use a bracket. We can go back to some of the notation that we use with inequalities. You could say this too. That works, right? Actually, we'll just say those two. You could say it either way. That's fine, right? What you're communicating there is every single real number is in that function's domain. You put a number in as an x, you'll get a number for your y. All right, here's a bunch more, right? I think I've got 8 of them. We're just going to burn through them. And all we're after here is to identify from the equation that function's implied domain. Okay, it's implied domain. Right away, on this next one, I see a line, and I don't hesitate. Again, you only need to write it out one way or the other, but just to reinforce the idea, right? You could say it either way, all real numbers. Okay, 1 over x. Okay, this is a case that you should look closely at, right? There's really 2 cases where you have to be very aware of some potential restrictions. If you have a fraction and x is on the bottom, you might. Okay, you might have some restrictions. Okay, you'll see that's coming up on the next 3. Okay. The bottom cannot equal 0. Okay, now here I don't have any work to do because all that's on the bottom is x. Okay, if I go this route, which you'll see that come up, x can't be 0. Okay, if I say that, I'm implying x can be anything else. Okay, and all I was curious about is what x values would make the bottom 0. What does 0 will? 1 divided by 0, that's going to be undefined. Right? So 0 is not in the domain. But you can say it that way. Anytime you're restricting the domain and you're saying the x values that aren't in it, you are implying that, again, it could be anything else. And that's the case here. You can put in any other x value besides 0, and you'll get an answer. A little more going on the bottom. Set that equal to 0. Solve it, right? X equals -5. X can't be -5. Okay, that's the way I would state that function's domain. Okay, X cannot be -5. Can be anything else. One more with a little bit more going on still. Nothing we can't handle. And we get that x is 0.4 or 2 over 5. Cross it out, right? X can't be 2 over 5. Could be anything else. That's a good collection of examples to have if you notice a function is written in the form of a fraction. Okay, now the function family is called rational. We haven't looked at those yet. Okay, other than today, we've seen them very briefly at times. We haven't really like dove in and said, hey, let's really look closely at rational functions. Okay, but they typically do have restricted domains. Okay. We see another one, right? That's rational. It's kind of a funky one. X squared is down on the bottom, which I'll take the same approach. Set it equal to 0. Take the square root, right? Square root of 0 is 0. And there we go, right? X can't be 0. Didn't change anything with, if I had a quadratic on the bottom, it doesn't change that I'm still concerned. Again, if the function is rational, that means if it's written as a fraction, specifically as a fraction with an x variable down on the bottom, I got to set that bottom equal to 0 and solve it, because those x values are going to be excluded from my domain. Okay, so here's the deal. This one's interesting, all right? I'm gonna break this one down. I was referring to this one earlier. It's a cubic function. It's a cubic, right? I got r to the third power, okay? There's no fraction. I'm not worried about the bottom of the fraction being 0. So if I want to, I could say all real numbers. Okay? However, I'm going to put a little disclaimer with that. That specifically would mean I'm talking about the implied domain, right? You put an r value in, you'll get an answer, right? This function will give you a real number as an answer. However, r is for radius, v is for volume, right? You may not recognize this, but I see that formula, and it's from geometry. I have to brush up on my geometry a little bit. I'm almost positive it's the volume of a sphere. That could be wrong, but I'm pretty sure it is. So you could take a different approach if the problem has a context. And I know on this one you see it and you're like, it wasn't really that clear the problem had a context. I thought maybe it's a volume formula, but I didn't really know. In a word problem, you can get into a practical domain where it's like, yeah, okay, you could put anything you want in for r, right? But here's the deal. If you're talking about r being radius, there's no such thing as a radius of 0. Like if you're actually calculating the volume of a sphere, there's no such thing as a radius of 0. There's no such thing as a negative radius. You could then say r needs to be greater than 0, okay? And that is what I was referring to earlier when I was saying you can run into problems where if it's a word problem or it has a context to it, the domain might be more restrictive, right? In theory, right, our implied domain, you'd say R can be anything. In reality, if you were doing this to actually make some calculations about the volume of a sphere, R is greater than 0, right? You wouldn't spend any time looking at negative R values. All right, last two, we get into the second major operation besides like division, all those rational functions we saw with division that can restrict our domain, and that's the square root, okay? Typically speaking, you've got to make sure what's underneath your square root is at least 0 or bigger, right? What is going to happen if we put in a negative? Right? We'd get i's. And if you went back to our definition for what has to be in our domain, we got to put a number in. Specifically, it has to be a real number for x. We need to get a real number for y. So we would not look at that case. Like we've seen it come up when we looked at quadratics last unit, and we've dealt with the square root of negatives, and we've done the whole I, the imaginary component in complex numbers, but for a function in its domain, we don't look at those, okay? So for that square root of x, I would say x needs to be at least 0, okay? Now here's the way you could do it. Take whatever is underneath the square root, okay? You need to set it up as an inequality that is greater than or equal to 0, and then you solve. And then for this one, x needs to be at least 7, okay? Got to be at least 7, okay? Because if I think about that, if I put in 6, right, I'd subtract 7, I'd end up with the square root of negative 1. Starting at 7, right, 7 minus 7 would be 0. So from there, I could put in anything bigger. All right, that's all for function basics. Little domain. In day 2, kind of more of the same. Some of the ins and outs and other characteristics of functions that we've kind of used but haven't addressed specifically yet.